Hello Techzone students, how are you all? In this video we'll study about gradient descent. In the previous video we have studied about ordinary least squares, isn't it? So this video is all about gradient descent. Alright, so let me draw a graph here. This is our x-axis and this is our y-axis. Let this be the data points. Okay, I'm just randomly drawing few data points, and our linear regression has predicted this line. So this is our best fit line. And what will be the equation of a straight line? Y is equal to mx plus c. Okay, of course you can write different notations also. Some write it as y is equal to beta 0 plus beta 1 x. Okay, but let us write it as y is equal to mx plus c. Okay, our linear regression model has drawn this line which is best fit for this data points. Okay, and this y is equal to mx plus c is also called as hypothesis function. Okay, now we need to find the cost function. Okay, cost function, or it is also called as error function. Okay, what is this? See, I'll explain you. Let me just change the color. Let me draw a graph here one more time. This is our x-axis and this is our y-axis. Okay, I'll take 2 points and explain you if this is the best fit line. Okay, now what is error or what is residual? See, if these are the values of x 1 2 3 4 and if these are the values of y 1 2 3 4 5 and so on like this, okay, this points are our actual values, but our model has predicted that this should be the line, isn't it? So when x is equal to 2, the actual point is how much? It is equal to 4. But our model is predicting that it should be equal to 3. So what is the error here? The difference, it is 1, right? Okay, that is called as residual or error. Okay, let us denote that by d1. And what about the second point? See, when x is around 3.5, okay, what is the value of y? It is equal to 2. But our model is predicting that it should be equal to how much? 3.5 something, isn't it? Okay, so this is much is the error. So let that be d2. So like this, for all the points we'll calculate the residuals, isn't it? For all the points, and we add those residuals, and that sum should be minimum. Okay, so d1, d2, d3 and so on up to dn. N is the number of observations. Okay, we add all this, but we don't just add this, we first square these distances or square. Let me explain you. Let us take these 2 points. Okay, few points will be above the line, few points will be below the line, isn't it? Now if we consider the points which are below the line as negative, like let us say this distance is -2 and this distance will be positive, right? Let us take that as +2. So if we just add that +2 and -2, the error will be equal to 0, right? Which means this line should pass through these 2 points, but this line is not passing through these 2 points, right? Because our error should be equal to 0. When will the error be 0? When the line is passing through the points, isn't it? But in our case it is not passing, but still we are getting error as 0. Okay, why? Because we just added this. Few will be negative points, few will be positive, right? So positive and negative values, if we add, we'll get a small number, giving us an impression that the error is less, but which is not the case, right? So to avoid that, what we do is we take these values, we square and add them. So this will be 4, this will be 4, it will be equal to 8. Of course, afterwards we are going to find the square root of this. Okay. So we need to square the distances and add. We need to square the residuals and add. And this error should be minimum. Okay. So d1 square plus d2 square, d3 square and so on up to dn square. That is our cost function or error function. Okay. So let us rewrite that error function. We can write that as I is equal to 1 to n, because we have 1, 2, 3, 4, 5 here, right? So I is equal to 1 to n di square. Okay. We have generalized this. Alright, but what is the value of d here? What is di? Okay, di is actually the difference, isn't it? It is the difference between the actual value and the predicted value. Alright, so it is the actual value and the predicted value, yi. It is the difference. So I is equal to sigma I is equal to 1 to n yi, that is the original value and the predicted value. Don't forget square. So this is our error function. Okay. Alright. Since we are adding n number of observations, we'll divide it by n to find the average error. Okay. Or the mean error. Okay. Alright. So what is this now? This is called as mean squared error or cost function. Okay. Why are we dividing by n? Because we have added n values here. So d1 square, d2 square, d3 square and so on, right? So to find the mean of that error, we are dividing it by n. Okay. And see, in some notations you must have observed it is 1 by 2n. Okay. Why? Why do we have this extra 2 here in the denominator? Because when we differentiate this cost function, this 2 which is in the power will come in the front. Okay. And this 2 and this 2 will get cancelled. Alright. So the maths will become easier for us. Differentiation will become easier for us. It is not mandatory to write this 2, but to make things easier, you can include this 2 in the denominator. So we'll include that. So mean squared error, I'll write it one more time. It is 1 by 2n sigma I is equal to 1 to n yi minus yi hat whole square. Okay, this is our mean squared error. Okay, I hope this is clear. Now what we'll do is I'll write this mean squared error one more time. 1 by 2n sigma I is equal to 1 to n. Okay, yi minus yi hat whole square. Okay, now our aim should be to minimize this. Okay, our aim should be to minimize this cost function. Okay, but how do we minimize this? By adjusting or changing the values of m and c. M and c. Where did this m and c come from? Y is equal to mx plus c, right? This part. But you must be wondering, we don't have m and c's here. If you observe carefully, there is m and there is c here. Okay. See, this is predicted value, right? So in place of this y hat, we can write mxi plus c. So it is 1 by 2n sigma I is equal to 1 to n yi minus, in place of yi, y hat, we are going to substitute this value mxi plus c. Don't forget square. So this is our cost function or mean squared error. Okay. So if we change m and if we change the value of c, mean squared error will change. Alright. So this mean squared error now depends on value of m and value of c. Okay. So if we adjust the value of m and c such that our mean squared error is minimum, that will be our best fit line. Alright, I hope this is clear. Okay, let me just change the color. Okay, we'll come back to this formula. Okay, let us take y is equal to mx plus c. Okay, let c be equal to 0. That means y-intercept is 0. If y-intercept is 0, our straight line should pass through the origin. See, what is y-intercept? See, y is equal to mx plus c. So this part is y-intercept, right? The point where the straight line is touching y-axis is our y-intercept. But here y is 0. That means it should pass through origin, something like this, right? This is our line. So it is y is equal to mx. Okay. C value is 0 here in this case. Okay. Alright. So I just wanted to explain you this because this will be useful in the next slide. Okay. So we have only y is equal to mx. Okay. Let us take some easy data points so that the mathematical part will be easy for me to explain and easy for you to understand as also. Okay, let us take these points 1, 1, 2, 2, 3, 3 and 4, 4. Okay, these are x values, these are y values. So this is 0, 1, 2, 3, 4, 1, 2, 3 and this is 4. So 1, 1 point will be here, 2, 2 is here, 3, 3 will somewhere be here, 4, 4 will be here, right? These are our data points. Okay. So we considered 0, c is equal to 0 and let the value of m be equal to 1. Okay. So y is mx, right? So this will be y is equal to x now. Not 1, y will be equal to x because m is how much? 1. Okay. Now if you draw this line y is equal to x, that line will be passing through origin like this and it will pass through all the points. Okay. So this is our best fit line. Alright. A predicted line passes through all the points. So if it is passing through all the points, what is the cost function or what is the error function now? It should be equal to 0, isn't it? Because there is no difference between this point and the predicted values. You can prove that mathematically also. It was 1 to n, okay, yi minus y predicted value, right? So here, see, first, see, actual value is 1, predicted value is also 1. Okay, so 1 minus 1 here, don't forget square, plus actual value is 2 and the predicted value is also 2. So it is 2 minus 2 whole square. Actual value is 3, predicted value is also equal to 3. So it is 3 minus 3 whole square. Actual value is 4 and the predicted value is also equal to 4. So it is 4 minus 4 whole square, right? And it is 1 by 2 multiplied by 4 because n here is how much? 4 because we are taking 4 points. So this is 1 by 8. 1 minus 1 is 0. This is also 0. 3 minus 3. 4 minus 4 is also 0. So it is 0 by 8. It will be equal to 0. So the error or the cost function is equal to how much? It is equal to 0. Okay. I hope this is clear. Now what we'll do is we'll draw a graph between slope, that is m, and error, that is cost function. So when m is equal to 1, what is the error? It is equal to 0. We'll come back to this point afterwards. Okay, 1, 0. What will happen if we change the slope? Okay, let me just take another slide and draw the data points one more time. This is 1, 2, 3, 4, 1, 2, 3 and this is 4, right? So this is 1, these are our observations, right? These are our observations. Okay. Now let m be equal to 2. So see, initially m value was equal to 1 and the line was passing through all the points, right? But now the value of m has increased, that means slope has increased, right? So let me just rub this. The slope has increased. So our new line will something be like this. See, y is equal to mx, right? So we have y is equal to 2x because m is equal to 2. So if you substitute random values of x, we'll get the values of y. Let us say x is equal to 1. So what will be the value of y? 2 multiplied by 1, it will be equal to 2. So 1 comma 2. So if you take x is equal to 2, what is y? Y is 2x. So it is 2 multiplied by 2, it will give us 4. So 2 comma 4. So these 2 points are enough for us to draw a straight line, right? So let us plot this. 1 comma 2 is here and 2 comma 4. So 2 comma 4 is here. So and it is passing through origin. So this will be our predicted line, which is y is equal to 2x. There is a lot of difference here, right? See, this is the difference, right? Error. This is the error. Okay. And similarly, you'll have error here, you'll have error here, right? Okay. Now, let us go ahead and find what is the cost function here. Cost function here was 1 by 2n sigma I is equal to 1 to n y original value minus y predicted value whole square. So this is 1 by 2 multiplied by 4 because we have 4 points here, right? 4 observations. So original value is 1 here. Okay, predicted value is 2. So it is 1 minus 2 whole square plus original value is 2 here. Okay, but the predicted value is how much? It is equal to 4. So it is 2 minus 4 whole square. Original value is 3. Okay, this is 3. Predicted value will be 2 multiplied by 3, it will be equal to 6. So 3 minus 6 whole square. Okay. The fourth point, predicted value, original value is 4, predicted value will be 8 because y is equal to 2x, right? So if you substitute 4 here, you will have 8. So let us go ahead and find this number. 1 by 8 divided by, so this is 1 minus 2 whole square, minus 1 whole square will be 1. 2 minus 4 is minus 2, minus 2 whole square will give us 4, and this is 9 and this is 16. So finally we'll have 30 by 8 and it is around 3.75. Okay. So if m is equal to 2, what is the error or the cost function? It is 3.75. So 2 comma 3.75. We got 2 points, right? What are those 2 points? See, 1 comma 0 and we have 2 comma 3.75. We'll plot these points. Okay. Let us do one thing. Let us take m is equal to 0 and check. Okay. 1, 2, 3, 4, 1, 2, 3 and 4, right? These are our x values, these are our y values. So 1, 2, 3 and 4. These were our data points, right? Okay. What will be the value? Now see, y is equal to mx plus c. We considered c as 0. We are considering m value as 0, right? So y will be equal to 0. So 0 means we will have this line. C is also 0 and y is also 0. That means we'll actually have a line which is on x-axis. Okay. Let us go ahead and find the errors now. These are the errors, right? Okay. So what is cost function now? In this case, 1 by 2n sigma I is equal to 1 to n. Okay. Y original minus y predicted whole square. So this is 1 by 2 multiplied by 4 because we have 4 points here, right? Original value is how much? 1. Minus predicted value is how much? 0. So 1 minus 0 whole square plus original value is 2 here, but the predicted value is how much? 0. Okay, y values we are checking, right? So 2 minus 0 whole square. Similarly 3 minus 0 whole square and 4 minus 0 whole square. I hope you are understanding this. So this is 1 by 8 multiplied by 1 plus 4 plus 9 plus 16. Same number again, right? So this will be equal to 30 by 8, 3.75. So if m is equal to 0, what is the error function? 3.75. So we have 0, 3.75. Okay, we have 3 points now. Okay, what are those 3 points? 1, 0, 2, 3.75 and 0, 3.75. Okay, let us go ahead and plot those. Okay, let me write the points. First one was 1, 0. Okay, and the next point was 2, 3.75 and the third one was 0, 3.75. Okay, let us plot point between the slope, that is the value of m, right, and error function. Okay, so 1, 2, 3, 4, 5 and how much is this? 1, 2, 3, 4, 5 and so on. Okay, so these are our x values, these are our y values. So when slope is 1, that is when slope is 1, I'll just change the color. When slope is 1, okay, what is the error function? It is 0. So 0 will be here, right? So that point, this point, right? When slope is 2, it is 3.75. So 3.75 will be here and 2 will be here. So something like this, right? When slope is 0, that means here 3.75, 3.75 here again. So if you join this, we'll have a graph which looks like this. Okay, we'll have a graph which looks like this. For our best fit line, see, for our best fit line, okay, error was equal to how much? 0. Okay, when was that? When m was equal to 1. Okay, let me go back and check. See, this was our best fit line, right? Because this line was passing through all the points. So when slope was equal to 1, the error was equal to how much? 0. That is the ideal scenario, right? So which part? This one. Okay. So this is called as global minima. Okay. See, for a best fit line, the error is minimum. And that point where the error is minimum is called as global minima. Our aim should be to reach to this point. See, we might start here, but this is not the minimum error, right? Okay, slowly we should come to this point where the error is 0 or very close to 0. Okay, I hope you are following this. Now let me explain you one more concept here. Let me just draw a line. This is our x-axis, this is our y-axis. See, if we have a straight line which is in this form like this, slope of this will be positive. Okay, see, let us take some random values. So let us say this is 0, this is 1 and this is 2. Okay, and this is 3 and this is 4, and here let us say it is 1, 2 and 3, right? So this point, and let us consider this point. What are these points? 2, 1 and 3, 2. So if you want to find the slope of 2, 1 and 3, 2, let this be x1, y1, x2, y2. We know that slope formula is difference of y, that is y2 minus y1 by x2 minus x1. So this will be 2 minus 1. So this 2 minus 1, 3 minus 2. So this will be 1 by 1, 1. So what I mean to say is, if you have a straight line which is like this on the right side, the slope will be positive. Okay. If we have a straight line which is like this in this form, the slope will be negative. Okay. You can again take random numbers. Okay. 1, 2 and 3, right? So let this point be 1, 3 and let this point be 2, 2. Okay, 1 comma 3 and 2 comma 2. So x1 y1 x2 y2. Slope formula y2 minus y1 by x2 minus x1. So what is y2? 2 minus 3, and x2 minus x1 is this. So negative slope, right? So if we have a line like this, slope will be negative. Okay, so using this concept we'll learn how the value of m will change. Okay, let us say we have a curve like this, okay, for m and for our error, okay, the same, this type of curve, okay, and randomly first we got a line like this, okay. Let us say that value of slope is m1, but ideally we should come to this point, right, this m, okay. So if we start from here, how will we come here? Okay, or if we start on this side, okay, this will be our line and this is m. Our aim should be to get to this value of m where the error is minimum, isn't it? So in this case, in the first case, if m is here, if we are starting on this side, on the right side of the curve, we should decrease the values of m, right? So here m1 we should go back, right, isn't it? So we should go back and we should come here. That means we should decrease the value of m. If we are starting on the left side of the curve, what should we do? We should increase the value of m, okay, to get to the global minimum, isn't it? To get to this point m. So here we need to decrease the value of m. Here we need to increase the value of m, that is slope. So who is going to do that? Gradient descent algorithm will come into picture in this. Okay, what? Gradient descent algorithm. Gradient descent means, see, imagine this like a mountain will come down slowly to the valley, okay, to the valley that is at the bottom. Alright, I hope this is clear. We use gradient descent algorithm, or it is also called as convergence algorithm, which uses gradient descent. Okay, what is that convergence algorithm? It is repeat until convergence. Okay, so we need to repeat this step until we come to the minimum value. Okay, so in the textbooks and in some other videos you must have seen some difficult formula for this, but let me tell you, this is very easy. M new, that is new slope, should be equal to old slope minus slope of the cost function. Okay, this much slope of the cost function, but we add learning rate to that. I'll explain you what that learning rate is and why we are adding it. So this is it, guys. This is the convergence algorithm. New slope should be equal to old slope minus learning rate. This alpha is the learning rate and slope of the cost function. Okay, let me rewrite that. What was cost function? Cost function was equal to 1 by 2n sigma I is equal to 1 to n y original value y predicted value whole square, right? Okay, so our m new, that is new slope should be equal to old slope minus alpha multiplied by this. This is what? Sorry, slope of this. Okay, cost function, slope. I'll write slope of this. How should we find the slope of any curve? Differentiation, using differentiation. Okay, so this is m old minus alpha differentiation. Okay, differentiation with respect to m and cost function. This is our cost function. Okay, if we differentiate this cost function, we'll get the slope of that cost function. Okay, minus alpha. I'll just write slope here because I want to explain you something here. See, let us say we are starting from here, right? Randomly our line is this, and this value of m is, let us say, some 50. Ideally we should get here, right? Okay, now just now we have studied that slope of this type of line will be positive, right? Okay, slope of this line should be positive. So here we have m new, that means we need some other point. Let me change the color, maybe a point here, right? So that will be our new value. So m new should be equal to m old, that is m old is 50 minus alpha. Alpha generally we take it as 0.01. Okay, 0.01 multiplied by slope, that is 50. Okay, okay, sorry, slope of the cost function, right? So slope of the cost function, that is slope of this line, so it will be what now? Positive. So what are we doing? 50 minus, even if you multiply 0.01 with positive number, here also we'll have a positive number, right? So 50 minus some number, that is something. Okay, so what will happen to this 50? It will decrease now, right? That means this m new will decrease. Decrease means it will come this side. Maybe this will be the new point, and in the next step it will decrease further. In the next step it will decrease further. Okay, like that it will come to the global minima. Okay, I hope this is clear. What I'll do is I'll just rub this part and draw one more graph here. Okay, so great. Okay, not x, it is actually m, right? So like this. So what if we start from here? This is our line. Okay, ideally we should get to this point, right? So just now we have seen that if we have a line like this, the slope will be what? Slope will be negative, right? So m new, see, this is m old now, right? So we should get somewhere here like this, right? We need to get to this point. So m old minus alpha multiplied by negative number. So here m old minus, this minus and this minus will become plus. So m old plus some value, right? So what will happen to this m old? This m new will increase now, right? M new will increase. So maybe it will come to this point and we'll get a straight line like this. And in the next step here, in the next step here, in the next step here, and the next step here. So like this will converge to global minima. Okay, so it doesn't matter whether we start with this line or with this line. Finally we'll reach to this global minima. Okay, using this convergence algorithm. Okay. Okay, I wanted to show you the visualization of gradient descent. So here we took the curve as x square. So this U-shaped curve is x square. Okay, if you draw the graph of x square, you will get a U-shaped curve like this. Okay, and what is our starting point? Our starting point is 5. So here this is our starting point. So initially it is 5. Okay, this is the slope of the cost function. This is slope of cost function. Okay, we are starting at 5. Now our main aim should be to reach this point, right? Global minima. So how do we reach that? How do we reach there? Okay, by slowly descending on this curve, isn't it? Like this. So see here, we took the learning rate as 0.01. Okay, it was denoted by alpha, right? So what I'll do is I'll click on next iteration now. Just see what will happen. Okay, I'll just clear the graph first. Okay, so see here what is happening. The values of m are changing and this straight line is coming closer to the origin, isn't it? That means it is coming closer to the global minima. So this is what happens in gradient descent. Okay, we started at plus 5 here. We started here and slowly will come to this point. Okay, now you must be wondering what will happen if we start from here. Let us visualize that also. So let us start this from -5. Okay, click on setup. See here. So we should go like this, right? We should travel this path slowly and come to this point, isn't it? Okay, let us see. So learning rate is same, 0.01, and see exactly what we were expecting, right? So slowly it will go and it will come to the global minima. Where the error is, I wanted to show you this. Okay, what was our cost function? Our cost function was 1 by 2n sigma I is equal to 1 to n. Okay, yi minus y predicted whole square. Okay, this, or 1 by 2n sigma I is equal to 1 to n yi minus mxi plus c whole square, right? Because yi hat value is what? mxi plus c. Where did this come from? From y is equal to mx plus c, right? Okay, this is our cost function. All right. So everything depends on m and c now. If we change the values of m and c, the value of cost function will change. Okay, so we need to find the values of m and c in such a way that this cost function should be minimum. Okay, should be the least. So how do we do that? See, we have two variables here, m and c. So we'll find partial derivatives now. What we'll do is we'll first keep c as constant and then partially differentiate this with m with respect to m, and then we'll keep m constant and then partially differentiate this with respect to c. Okay, so little bit of maths here. All right, let us first find, see, let's calculate partial derivative of cost function with respect to m. Okay, let that be some dm. So that dm will be equal to partial derivative with respect to m. What are we differentiating? This part, right? So 1 by 2n I is equal to 1 to n. This is yi minus mxi plus c whole square. Okay, so 1 by 2n is common. Okay, So this sigma I is equal to 1 to n, this partial differentiation will go inside, and this is like a minus b whole square, so I am expanding this. So plus c whole square minus 2yi mxi plus c. Okay, I am using this a minus b whole square expansion. It is a square a square minus 2ab plus b square, or you can write this as a square plus b square minus 2ab, right? Same thing. Okay, after this, okay, what do we have? See, partial differentiation with respect to m, I is equal to 0 to m. Okay, we have yi square plus mx1 square plus c square plus 2mxic minus 2 okay yi mxi minus 2yic. Okay, this term. See, let us go back. See, I expanded this using a plus b whole square and then multiplied these terms. Okay, so yr square plus this will be m square xi square, okay, plus c square plus 2mxic, and these two terms are multiplied. Okay, so we'll get this finally. Now when we are differentiating with respect to m, so this will become constant, right? So this is 0 because it is not having m value. This will become 0 and this will become 0. So three terms will become 0. And if we differentiate this, partial differentiate this, what do we have? We need not write differentiation again. That is dm will be equal to I is equal to 0 to n. Of course, don't forget 1 by 2n. 1 by 2n here also. That will be equal to 2m. See, this 2 will come in the front. So 2m xi square plus, for this m will go right. So this will be 2xic. Okay. And this one m will go 2yixi. And if you take 2 common and bring it outside, it will be like this, right? mxi square plus xic minus yixi. So this 2 and this 2 will get cancelled. So see, that is the reason why we divided by 2, okay, which we learned initially, right? So it was 1 by n, sigma I is equal to 0 to n. Okay, can we take xi common from all these three terms? Of course we can. So xi common. So what will be left now? mxi, because we have xi square here, 1 xi we took out, plus c minus yi. So in other words, we can write this as xi multiplied by c. What is this? mxi plus c, this is y hat, right? Minus y, okay, original value. So this is the value of dm. Okay, this is the value of dm. Okay, now why are we finding this? See, we'll find this value because we need new m, right? New m should be equal to this, new slope should be equal to old slope minus, okay, learning rate and this dm, right? This is how gradient descent will work. Okay, all right, we found the value of m. How should we find the value of c? That is y-intercept. Remember, equation of the straight line will change if we change m and c, isn't it? Like y is equal to mx plus c. So if we change c and m, equation or the form of the line will change, right? So we know how to find the value of m now. We know how to change the value of m. How should we change the value of c? Same concept again. Now what we will do is, we will partially differentiate, okay, the cost function with respect to c, keeping m constant. So let us call that as dc. So dc is equal to partial differentiation with respect to, okay, c of what? Cost function. So this is partial differentiation 1 by n sigma I is equal to 0 to n 1 by 2n, sorry, 1 by 2n. Okay, yi minus, this was like this, right? And we squared that. So 1 by 2n sigma I is equal to 0 to n, and expand this, yi square plus mxi square plus c square plus 2mxic minus 2yimxi minus 2yic. Okay, this is the expansion. Now partial differentiation 1 by 2n sigma I is equal to 0 to n. So if we are differentiating with respect to c, so this two terms will become 0 because we don't have c in this, right? Okay, what else will become 0? This will become 0. So we'll have only 1, 2 and 3 terms. So what are those 3 terms now? C square. So what will c square be? C square will become 2c plus this c will go off 2mxi minus 2yi. So this c will also go, only 2yi will be remaining. Okay, so if you take 2 common, sigma I is equal to 0 to n, it will have c plus mxi minus yi. So this 2 and 2 will get cancelled, will have 1 by n sigma I is equal to 0 to n, and this is mxi plus c. Mxi plus c is what? Y hat minus y. Okay, so this is how we need to find the value of dc. Okay, I hope this is clear. This is the value of dc. Okay, see, new coefficient, new y-intercept is equal to old y-intercept minus learning rate multiplied by this. Okay, differentiation of cost function. So this is how we'll find the value of y-intercept. So this is how y-intercept changes, and this is how the slope changes. So if m and c, that is slope and y-intercepts, are changing, our linear regression will find the best fit line. Okay, so this was a lengthy video, but we have covered everything. Okay, each and every minute mathematical part of gradient descent. Thank you so much for watching the video.